development of new ceramic and photocatalyst materials. And I'm Toni Iborra, I'm responsible for the materials department at the IT3D Group. And I'm going to start this webinar focusing on the 3D printing process. Specifically, I'm going to talk about the advantages of using pellet 3D printing compared to traditional filament 3D printing. Because as you know, traditionally, filaments 3D printers have been used. However, in the last 5 years, we have seen a trend on this field towards the pellet 3D printing. So, what are the advantages of this technology, also known as fused granulate fabrication? Well, in order to the first one and the most obvious one is the wide range of materials. That means that we can work with more materials compared to the filament 3D printing industry. Why? Because in order to produce filaments, we use pellets. We use injection molding grade pellets. So if we use a pellet or a miniaturized version of a pellet extruder, we can use injection molding grade feedstock, and we can also develop our own materials in the same way as Colfeed4Print is doing. They are developing their own materials. After my talk, Pablo is going to be focused on this process. So as you can see, we work with common thermoplastics, typically used in the filament industry, such as PLA, ABS, PTG, but then we also work with more advanced materials and also some materials that in some cases do not exist as filaments. Let's talk about highly loaded ceramic materials that cannot be filamented due to the high loading percentage of inorganic material, or thermoplastic elastomers with relatively low sorting rule. Thermoplastic elastomers that are very elastic and therefore cannot be filamented. So instead of using the filament 3D printing technology, we can use pellets. We also work with polycarbonates, with polypropylenes, also polypropylenes with carbonate, glass fibers, and different additives with polyethylene, high density polyethylene. We also work with chlorinated polymers such as PVC and PVDF, and sometimes we also have done some work with high performance polymers. So the third advantage I would like to mention is the higher flow rate deposition. Why? Because with the filament technology, typically the filament that we use is 175 millimeters in diameter or 2.85. And however, if we use pellets as feedstock, we can use different nozzle diameters, starting at 0.4 millimeters to 5 millimeters. And therefore, if we increase the diameter of the nozzle, we increase the flow rate of the material. Another advantage is the reduced printing cost, especially if you want to work with standard polymers. One is this, because filament typically 2, 3, even 4 times more expensive than the pellets. And this, of course, makes sense because the feedstock typically used for the filament production are the pellets. So if we are using the pellets instead of the filament, we are reducing the printing cost. And this makes sense if your goal is to print big volumes of 3D printed structures. Another advantage of the pellet technology, and actually our technology, our 3D printers, is that we can also produce multi-materials structures. That means that we can combine up to 4 different pellet extruders in one device, allowing for multi-material 3D printing with mode or mirror printing. That means that you can print the same steel file at the same time with 4 materials at the same time, reducing the printing time again and increasing the efficiency. So if we do a quick comparison between the fused filament fabrication compared to the fused granulate fabrication, we are gonna see that for the pellet 3D printing, we can have custom composites, and therefore we can have custom materials, custom ceramic or metallic loaded materials, cost saving because we are avoiding the filamentation process, but a limitation that we can sometimes experience is some limitation on the final quality surface or the geometry of the 3D printed parts, mainly because the control of the flow rate is slightly more complicated compared to fused filament fabrication, which offers low cost because typically FFF 3D printers can be pretty affordable. You can buy them online for 500 euros, and you can get really, really, really highly detailed geometries. The main limitation of filament 3D printing is that some materials cannot be filamented, and therefore research and development is limited. So how do we use the feedstock? In order to use pellet feedstock, we need to use a pellet extruder. Okay, so we have developed a screw-based pellet extruder with two heating points that allows us to process thermoplastics as pellets. So here you have a schematic of our pellet extruder. You can see that we have a screw with a specific morphology in order to promote the compression of the mold of the melting material, and we have two heating zones. We have a heating zone at the upper part of the pellet extruder and a heating zone near the nozzle. And in order to obtain a good extrusion, we need to have a good selection of those heating those temperatures, both heating zones. So typically, the temperature that we are going to use for the heating zone number one is the glass transition temperature of that polymer, because the goal at the upper part of the extruder is to soften the material without melting it. While at the heating zone number two, we typically use again a temperature slightly higher than the melting point for that polymer, because we want to melt the polymer. If those temperatures are correct, we are going to get a consistent flow. Therefore, if we compare filament 3D printing to 3D printing, the slicer for filament 3D printing, the slicer is going to calculate the volume that needs to be deposited per layer based on a filament with a specific diameter, 175. So the slicer can precisely calculate the volume using the volume formula and using 175 as the diameter. However, the main challenge that we experience when we are doing pellet 3D printing is that we need to use a multiplier because our feedstock is not filament. We are using pellets. So we need to use a multiplier in order to adjust the flow rate. And this is a value that we typically obtain experimentally. And finally, the surface quality of the 3D printed will depend on four factors. It's the rheological and thermal properties. That means how the polymer is behaving when melting on when it's under a compression effort. Also, the pre-drying. So we need to make sure the highly hygroscopic materials are dry in order to remove moisture. Because if we do not remove moisture, these kind of water molecules are going to appear on the surface, decreasing the final surface quality. The pellet morphology, as I always like to say, our pellet extruder was designed for injection molding grade pellets, but we have realized also together with our colleagues from Colfeed4Print that we can push the boundaries of our pellet technology, pellet extruder technology, and at this point we can process some pellets. We have done some tests with ceramic powder from Colfeed4Print. I think Pablo is going to talk about this later, but we were able to process this material. Actually, it was a PLA polymeric matrix loaded with aluminum oxide. And also we have done some work with zinc oxide ceramic material too, and we got very consistent and very detailed structures. And finally, the flow rate. As I said before, this is the critical parameter that is going to determine the surface quality of the 3D printed part. It's a value that we obtain experimentally and that needs to be adjusted. This is why I always like to consider pellet 3D printing as an advanced fabrication technology. So we work we work actually with Colfeed4Print. We have tested their materials. Pablo will explain how they synthesize these kind of materials and also the different ceramic materials that they have been playing with. And our goal here was to validate their materials with our pellet technology, and our results were really consistent and were really good. we were able to present um, materials with a high percentage of inorganic ceramic content. However, I'm gonna let now Pablo to explain in detail about their materials, about their compositions, and also about the synthetic process. So, Pablo, feel free to go ahead. Thank you very much.
Okay, so I will try to share the presentation. Thanks, Tony, for your presentation. And so what I think that now you can see the presentation and actually you can hear me well. Well, good morning, everyone. Thanks, first of all, IT3D for the possibility to participate in this kind of webinars, and in particular to Dr. Toni Iborra for this previous presentation. As he said, my name is Pablo Ortega, and I'm the Printing Research and Development Manager at Colfeed4Print. And in this slide, you have actually our contact information in any case that you want to ask something about our materials. So I would like to begin the presentation by introducing Colfeed4Print, okay, and specifically what we do. So we are a startup of the Spanish National Research Council that signed 2020. We are producing high value add composite materials for thermal extrusion technologies. In this slide, you have a really simply scheme, but it's just in order to understand the relevance of this type of materials and actually this type of technology in the processing route of the traditional way in the ceramic processing route. Okay, so just introducing these 3D printing technologies, we're able to have some shortcut in the processing ceramic pieces, and also giving the solution that the challenges this industry, okay, such as the freedom of design in complex structure, also the easy prototyping of this complex structure, and in our particular case, the processing of any kind of material by the thermal extrusion material technologies. That is why it's common to find this type of 3D printers in different industries, such as biomedical, automotive, food, construction, between others. And actually, our identity hallmark and what distinguishes us from our competitors is our patented wet mixing process, okay? Because in the traditional thermal mixing of composite materials, we are talking about mixing that requires more raw materials and actually more energy consumption, and whose dispersion of the organic inorganic phases between others is more difficult. So in the wet mixing route, we are able to use ceramic nanoparticles, increasing their content. As Tony told us before, there is an advantage of the use of hopper systems, and actually how we can manufacture custom composition because we reduce the quantity of the material that we are producing, and actually we reduce the energy all of the process. In our particular case, the initial product that we are producing are granules that has this shape, okay? So we are, I mean, it's not necessary in our case to reverse the extrusion process for process pellet for the hopper systems. And this is also particular because we are able to customize the primary side of our granules, trying to increase the fluency and actually to increase the fit ratio of our morphed material during the printing process. Obtaining, as you can see in this slide, different millimeter fraction, but actually we have in catalog that are between 1 to 3.50 millimeters because we have tests that are the more suitable to facilitate this fluency and actually this fit ratio that I was talking before. And actually, something more about our processing route is that We use PLA as a thermoplastic matrix, so our materials are neutral carbon footprint with much less energy consumption than traditional thermal mixing, and actually in a totally circular and sustainable process, because we are not only able to reevaluate waste particles from other industries, even metallic or ceramic, but actually we are able to reevaluate the printing and production errors, producing again the granules that we can extrude into filaments and actually that we can directly use in these hopper systems. So here in this slide, you can see an overview of our catalog with different particles depending on the main industrial application. And we will see some examples below. For example, in the line of the ceramic granules and filaments, we are talking about materials that are able to produce different components, industrial components, drills, dental crowns. Actually, we have an eco line that we are talking about nanoparticles for the energy sector, that we are able to print water and gases filters. Actually, we're able to print different battery parts or even fuel cell parts. And in the health line, we have a registered material whose composition allows us to print biomaterials to be used in regenerative engineering, pursuing the printing of custom implants and reducing the patient recovery times and also the rejection of this type of implants, and always working to make them economically accessible to more people in society. As new developments, we have this structure that are called for the printing, that is just the functionalization of our 3D printed parts. And from an electrical or mechanical impulses, we're able to generate this response on the 3D printing parts. And now we will move to the part of the printing parameters that we are using in this kind of materials and try to explain why this why make this type of decision and to improve your experience with these materials. So here we have collected main parameters involved, and I will try to explain how to optimize them. Okay, so one of the main advantages of the hopper, as Toni told us before, is that we are able to change the diameter of the nozzle. Actually, this is directly related to the feed of the ability of the system to feed the material to the motor itself. So we can change the motor steps and we can control the temperatures and the extrusion ratios. With all of this, in this example, we have the printed granules of alumina component, okay, with different nozzles. Keeping the temperatures and the extrusion ratio constant, we just need to increase the motor steps. And this is because we need to keep the molten material always fit and try to flow better, to put more material on the nozzle. And actually, in this nozzle, we need to study the shear rate that our molten material is acting. So we can explain this in this following slide. Because first we need to know the melting temperature of the materials from a thermogrammetric analysis, okay? And we will evaluate their melting behavior in terms of the deformation, frequency, and also temperature to ensure that the thermoplastic of our composite material is viscous enough to guarantee the same dispersion that we achieve during the wet mixing route. And from this, we will be able to establish like a printing window where playing with the optimization of the hopper parameters mainly affected, we will obtain high quality parts without compromising the solid contents of the final part. That is quite important for the sintered materials, and actually without making any bad choice of temperature or printing speed. For example, in the same case above, using the same motor steps, it will be necessary to decrease the temperature of the second, the higher thermocouple, okay, in the hopper system, just to make more solid the material and increase the fluency and the feed ratio of our molten material. Another option could be just to increase the extrusion ratio over 105%, keeping the temperature constant. And this is the same effect in which the nozzle feed and the melted material ensure good qualities of the final parts. These printing parameters have a direct impact on the consolidation of the 100 ceramic components, as I told you before. And during this presentation, I have talked about sintering, supposing that everyone knows that is the process without melting the particles, we are able to form necks between them to consolidate the 3D printing piece. And thanks to these wet mixed materials, we can see how the binding and sintering process make easier because we reduce the number of steps. Actually, it's not needed solving the binding. We also reduce the time and the energy required to obtain the consolidation of our ceramic particles. And also in the sintering process, the size of the particles contributes significantly to the sintering, as I told you. Since the smaller the particles are, the more surface area to generate necks and the lower energy required for the formation of necks. So reducing not only the sintering times, but also the sintering temperatures. Here you have a scheme of one of our sintering process that in less than 20 hours, we're able to obtain this green piece that we can show in the slide in the left part to the sintered one in the right part with obviously a shrinkage of the sample. So now we will talk about the structural characterization. Here you can see how ensuring these molten behaviors and keeping this temperature, these parameters during the printing process, we're able to obtain ceramic pieces with a really high resolution. And as I told you before, after the sintering process, we have a shrinkage. So it's something that we need to take into account when we prepare the green sample, okay? And in our materials, we're talking about 20%, 25% of the shrinkage in all aces, okay? And here you have some images of the section of our materials. These are from the green part that keeping this molten behavior, you are able to obtain this type of structure. And actually how after the sintering process and going a bit deeper in magnification, we can see how we eliminate completely the polymeric matrix and actually how the particles are able to form this network and consolidate the pieces. As a last example, I will talk about materials with high electrical conductivities, okay, are not sinterable, but actually with the composite material, you will perform like really electrical conductivity pieces. And these are within the eco line in our catalog, and we can verify how ensuring also this molten behavior will allow us to obtain this kind of a structure. In concrete, we will be talking about the graphene and the graphite materials that we have in catalog. And you can see with the scanning electron microscope images how are nanometric, but actually has a form factor that makes them micrometric in one of their dimensions. Okay, and actually this difference in the specific surface area makes the difference in the electrical conductivity of both materials. Materials that allow to reach different electrical conductivities depending on the particle content. And although I would like to point out how the material with 50% in volume of graphene and the rest of PLA reaches electrical conductivities in the same order of magnitude as the shielded prints, just in the filament. So the printed parts should be higher. In this slide also, you can observe some interesting properties of carbon-based materials, such as the high electrical and thermal conductivity, also the efficient absorption and the high catalytic performance, the improved mechanical properties together with the chemical stability that make them suitable for different industrial applications. And actually, keeping in mind that has this different in the size of the particles. We have again the same parameters during the printing process by a hopper system in which we use the same nozzle diameter, but in this case, because of the size of the particle, we need to increase the motor steps a little bit, keeping the temperature sound extrusion ratio constant. This ensures the structurability of these materials within the printing process and allow us also to take advantages of the fact that with these temperatures and molten flow, we are able to orientate the nanoparticles parallel to the printed molten material and obtain different structures depending on the orientation of the part in the bed of the head of the printer, obtaining high quality structure not only for the energy sector, but as we can see here in the slide, we are opening to different industrial application. In the case of the graphene, not only the energy of batteries, of fuel cells, also of prostheses, biosensing, nuclear medicine, even solar cells. And that's all. Thank you very much for your attention. And again, I leave you the contact information in case you want to consult that, and also invite you to follow us on social networks so that you can be updated with all our news about the technology and also about the materials. I don't know if you have any question, but now we have time to talk about it. Toni, are you there?
Yes, I'm here. I was struggling with the audio. So thank you very much for the presentation. Um, Now we are gonna start with some questions. So do we have any questions that you want us to clarify? This on the future of what is the price? Hi, Robert. What do you mean by the fuser? Do you mean the pellet extruder or oh? So we commercialize the whole 3D printer. So at this point, we are not commercializing the pellet extruder itself because from our experience, we have realized that the integration to a new device is pretty complicated. So we are offering just the full 360 solution. And we have different sizes. We have small 3D printers for research and development, and then we also have 3D printers for bigger volumes. Say. Thank you, Robert, for your question. Do you have any other questions? No? Okay, so Pablo and everybody, thank you so much for your time, and I hope to see you again in the next webinar. Thank you, Pablo, and thank you. Bye.
Bye, guys.